talk is an abbreviation of the splinter session that was given in Seattle, specifically to address the fundamental, the existential question of can we realize a 4.5 Kelvin telescope? Lots of people say, gee, Webb was a hard telescope and it was 40, and thinking in absolute terms, this is roughly 1/10 the temperature, so it must be 10 times harder. And so we have come about looking at this problem from two very different directions and come to the same conclusion. So Mike DiPirro, who's here present, will present the first, essentially, from scratch design, and then I'm going to take the Webb design and show you an argument for, with certain modifications, that telescope can also be repurposed for the purpose of being a 4.5 Kelvin telescope. And because we've got multiple answers coming from multiple different directions, we conclude that such a telescope is feasible. Moreover, it's within the state-of-the-art coolers at a finite number, which is accommodatable in current spacecraft for a reasonable amount of electrical power. Mike?
So I'm going to be talking about the baseline design that's in the report. John's JWST-like design appears in appendix. Do you remember, Margaret, which appendix? Yes. Oh, I thought that was already settled. Okay. All right. Anyway, John's will also appear as an appendix in the report. Oh, okay. At the end of Appendix C. No, it isn't in Appendix C now. I thought it was going to be in its own appendix. How long? Okay. Yeah. All right. So I'll be talking about what's in Volume 1 in the main body of the report. And just to reiterate John's question, we've got, from the face of it, a problem that's 10 times harder than JWST. But if you were to look at architecture that looks more like Spitzer, this is here, Spitzer got down to 5.5 Kelvin. They did use liquid helium because cryo coolers that got down to that temperature were not ready yet. But they had something that looks like us, although much smaller. So let me go back to this. So now we have cryo coolers that are more mature. We have the ACTDP technology advancement of cryo coolers to get down to 6 Kelvin. It turned out to be for JWST, and the Northrop cryo cooler is now TRL-7 and ready to fly. And that produces pretty close to the power that we need per cooler for our design. So we decided to say, let's take the coolers that exist now, advance them a little bit so that they get down to lower temperature with the same cooling power, same input power, so approximately the same compressor that we're already using, and then let's cool a bigger telescope. So how many of these things do we need? One of the things about us that we don't have to worry about as hard as JWST had to worry about is vibrations. And that's one of the bugaboos, let's say, of a cryocooler, although there are some small vibrations in other things too. Certainly in spacecraft things, there are vibrations from reaction wheels and things like that. So we just need to be lower than other things that we know how to mitigate with soft mounts and stuff like that. We are that. Unfortunately, I don't have that slide in here, but we have a slide that we should add to the deck that shows a very first level calculation that shows our jitter is very, very low compared to our requirement. Low temperature has a lot of advantages. It's hard to get to, but once you get there, then there are a lot of advantages. The thermal contraction once you're there is so small that even large temperature gradients, first of all, you can't have a large temperature gradient if you're already at 4 Kelvin. You can't have a, well, I guess you could have 4 to 8, but if your average temperature is 4, you pretty much have 1 Kelvin or less temperature gradient in it. That would be negligible, but we only have millikelvin temperature gradients in our design because the heat that we're allowing to get down there is so small. So the top level architecture, and the reason why I'm standing here instead of a different kind of engineer, is driven by this cryogenic need to get to low temperature. So that's why it looks the way it does. That's why the baseline design looks the way it does. Could have looked like JWST, and John's going to show you that, and it'll still work. But we went a different way with a different paradigm, and that's something that has a baffle around it, and it looks like Spitzer, basically, a really big Spitzer. We can take advantage of the low temperature to use superconductivity, not only for the detectors, but also for mechanisms and things like that, where they become practically dissipation free, and that in turn means less cooling, and so sort of self-consistent solution. We stage our cooling, and I have a word chart after this. We stage our cooling so that the coldest things are inside and there's no warm things inside with the cold things. It only goes from cold to warmer to warmer to warmer to warmer. The electronics all sit down here in the spacecraft, the warm electronics. We have amplifiers attached to the instruments at low temperature that get our signals up. So instead of putting a very short cable with a very warm thing next to something very cold, we put an amplifier that doesn't dissipate too much at the cold and then have a reasonable signal over a longer cable. So we can separate then the cold things from the warm things. That's very important for achieving a efficient, low power, relatively low power system. So this is what I'm talking about. So we start with a sun shield, in this case a 2-layer sun shield. JWST is a 5-layer sun shield, but that's because it's all shiny surfaces and radiating out the end. If we don't need to do that, and Spitzer, they had a 2-layer sun shield, and have a dedicated black sun shield, I think maybe JW could actually do this, then you can get by with just basically 3 layers, 2 layers of sun shield and 1 black thing on the other side of it. So that's our deep space radiator. Spitzer got to 34. We know this is doable. And so that we're saying we're getting to 35. Actually, our thermal model says we get to 35. We use a cryo cooler that provides 3 stages of cooling. Again, the temperature is a little bit different from JWST, but that's with a modest development we can reach that. 20K is the temperature that JWST cryo cooler gives. And then 70K is a theoretical number. The cooler actually produces that. We just don't use it on JWST. And then for the detectors, we need much colder. 4.5 is good for background. In other words, the telescope doesn't emit very much if you're at 4 Kelvin and it's shiny. But the instrument detectors need to be way, way colder because of sensitivity considerations. They only get sensitive. In fact, a very, very large improvement in their sensitivity could be if we extend this 50 millikelvin down a little bit more, say 35 millikelvin, which is feasible. Certainly it's possible. We can use a JWST driven chamber, modifications on Johnson's historic chamber A. We fit in there. The temperature of the shrouds can actually go down to 11 Kelvin. It's been demonstrated. And if we ask them to and they change the software, they can go down to 10 Kelvin. But that provides very good background for this radiator, which is what we need. Over the aperture, we'll have to provide some sort of cover that will have targets in it and things like that so we can do ground testing. So the cooling power of the cryo coolers and the higher internal thermal conductivity also allow us to cool down very rapidly. So compared to JWST, our cool down times will be maybe a third of theirs. So instead of taking about a month, it'll take about 10 days, maybe 7 days to cool down. So we can cool down, and if we are careful about how our contamination sources are placed, we can warm up very quickly with this system. So the turnaround time and therefore some of the cost gets more modest. So here's our budget. So 100 milliwatts is what our design says we need. We always put a factor of 2 margin on that, so we actually are sizing the coolers for twice that. Spitzer was 6 milliwatts, but 6 milliwatts on a helium system is challenging. I mean, 6 milliwatts is challenging, but to make the helium system last for 5 years, you need a pretty big helium tank. For 100 milliwatts, obviously 16 times as big a helium tank, that's going to start to be really challenging. And it's more than that. The care and servicing of helium dewar on the ground is very difficult. So beside being a limited lifetime item, you also have much more complications in making contact to the things in there, demonstrating things on the ground, because the dewar can't surround the telescope. It's just that would be way too big and too heavy. So the cryo cooler is actually the right solution for the problem. And we've just now technologically reached the point where we can make use of cryocoolers instead of liquid helium to do this. The other parts of the thermal model have also been scoped out. We need 1.8 kilowatts, which is a lot of input power to run these coolers, but actually the 2 instruments need about the same amount. So we're not that far off from being a power hog here. And we keep our 100% margin, which gives us some conservatism. Here are 5 examples of cryo coolers that have reached, in the case of the Sumitomo cooler, have reached 4.5 Kelvin, these space flight coolers. Obviously on the ground we can do way, way better than this. It's making things smaller for space that is the challenge. So Sumitomo has one that's already flown. Miri will be flying soon. Lockheed, Crieri, and Ball also have cryocooler candidates, and we envision a technology development program that includes all of these to mature to a high TRL in time for origins. To get to the lower temperature, we, again, ADRs, adiabatic demagnetization refrigerators, have flown. They flew on XRS, although that didn't make it to orbit, XRS-2, which made it to orbit, and the ADR worked fine. Hitomi, which made it to orbit, the ADR worked fine, the detectors worked fine, and so now we have essentially XRS-4. The detectors are still state of the art, even 2 decades later, and the ADRs have advanced, so now they're more efficient, but we need another order of magnitude in cooling power from what they've already done. So this is like a single shot ADR if you want it to last a long time. You want to have a high duty cycle, 0.4 microwatts. We need 6 microwatts because they're cooling huge arrays with lots of wires coming in that are parasitics. So, but we have already demonstrated that in a laboratory version that was developed, again, a couple decades ago, and currently being moved forward, raising its TRL from 4 to 6 by an SAT that will be completing this year. And we can do not only the 6 microwatts, but we are only rejecting 6 milliwatts to the cryo cooler, and so the cryo cooler, that's not much of a load compared to other things. Magnetic shielding, we only need to get the fields down to sort of earth fields so that the detectors are not affected by it. The detectors have their own shield. And so this should be easily achieved, and our mass is reasonable. And this is what it looks like. And this is just our artist concept, so we weren't worrying about how big or small this is. This looks pretty big here, almost 1/2 meter tall, but when you see it in the context of the two instruments that use it, they're pretty tiny. The instruments are huge. So this doesn't need to be shrunk, but can be, because here are the components inside it. And so those can be redistributed, and it's just the outer conceptual shield that made it so big. So to summarize, take the Spitzer architecture, use cryocoolers that are now being developed, and with a little push from technology development in pre-phase A, we'll get up to the required TRL for origins. Sub-Kelvin coolers are already under development, and a little extra push. Not only will they reach TRL 6, but we'll probably be able to push the temperature down that we can lift to 35 millikelvin, helping the detector sensitivity out. And we can use chamber A because we fit. So turn it back over to John.
Okay, so I came at the problem slightly differently, looking at the possibility of establishing a JWST-derived design for OST. So basically, I gave the problem to my thermal architect, and I gave him the following instructions, basically to avoid changing anything that wasn't necessary. Now, Mike went over a number of really excellent design points for cryogenic systems, namely get hot things away from cold things, some of which exists on Webb, which is part of the reason it was quite as challenging as it was. We did have to keep room temperature electronics relatively close to the detectors, putting basically 230 watts on the cold side, forcing us to literally build a sun shield around it. We would use current technologies such as heat pipes to get heat away efficiently. Again, the idea is to leave as much of the bones of the design of Webb alone as possible. Keep in mind, about 2/3 of the program cost was spent getting the system design complete. We want to reharvest as much of that as possible. This approach allows us to take the instrument electronics that are currently on Webb's cold side, move them into the spacecraft, also dissipate the heat in the thermally challenged spacecraft into a room temperature radiator that you'll see has been added to the Webb design to accommodate the few cryocoolers that we need to cool the telescope. And then we did look at, as a last resort, to use actively cooled intercepts, which is a holdover from our first look at this design in the far forgotten days of Sapphire. So the idea of reusing JWST is not new. In fact, it's about a decade and a half old. So the thermal modeling approach, which was a little bit different than Mike's, uses the validated Webb thermal model. So essentially, we watched where the heat flows were and looked to interrupt them in a determinative fashion. And then the OST thermal modeling, we wanted to eliminate things that we did not need beyond the baseline. So things like the instrument electronics component, this is the hot electronics component, was moved. We don't have a harness radiator, so the harnesses that go from the warm instrument compartment to the cold instruments on Webb actually have an additional radiator to passively dump heat. That's hardware that was taken off. There's a deployable radiator on the ISIM that has been removed, and basically a lot of the insulation allowing good views to space. We did use the thermal performance parameters from the blankets that were measured for JWST, which represents the current, we believe, state-of-the-art understanding of how well blankets behave at these cold temperatures. So the ISIM is fixed. The instrument radiators that are on the side of the ISIM have been removed. Promise you a deployed room temperature radiator for managing the heat. Cryocoolers that we're going to add to the spacecraft. Quick cold side. Side is looking at something warm or
Can you speak near the podium microphone, please?
thank you. I guess I will use the fact that I've got this long stick. Basically, the Webb Webb spacecraft is always in the sun, and we have to add radiator shields here to protect it from being overloaded, the second surface radiators from the sun shield. Let's see, and we've already stated that we're going to move the instrument electronics into the spacecraft. Very much along the lines of Mike's design guidelines. Right now, we can't essentially accommodate a significant increase in power with the current design, so we had to add the radiator, and then we would transport the heat out of the spacecraft to this room temperature radiator by capillary pumped loops, essentially heat pipes. We did also take a look at the necessary advancements to get the demonstrated 6 Kelvin cooler to 4 Kelvin. This follows up experiments that were done at Northrop on IRAD for the International X-ray Observatory about 10 years ago, where an additional stage was added to the cooler, which provides the additional step down from 6 to 4. We also did an initial assessment of the working fluid in the cooler. Could we use conventional helium-4, or do we have to go to the more exotic helium-3? We don't need the exotic helium-3, although it does provide some system advantages. I'm sure Mike's design, the baseline OST, would probably have a similar result. So when we look at the modification of insulations necessary, we come up with essentially about a watt at the 18 or 20 degree stage. Again, we're also using a set of staged coolings. This is a combination of thermal efficiency and architecture, and about 200 milliwatts at the 4 Kelvin stage. This can be done for a set of about 3 to 4 coolers. We can also come up with some other architectures where we have some additional intercepts that perhaps could lower that number further, but it introduces other complexities. And at the first look level of this design, just establish if there was a design or not, this we felt was sufficient. So basically, in summary, to summarize both what Mike and I had come up with, we believe that we have 2 independent designs that will achieve cooling on a 6-meter class mirror to 4.5 Kelvin for 3 to 4, depending on how you shave the uncertainties, state-of-the-art coolers with essentially high TRL modifications already understood. So with some development, engineering development, not technology development, certainly believe that realizing a 4.5 Kelvin telescope of this size is feasible.